Welcome to this unit on calculus. It's just a preparation lecture. When I was thinking about this lecture, I thought, what are the 10 most important results in calculus? And I came up with this following list. I hope you can see it on the board. And I want to say just something about it. It's for me also important that the result is applicable and that it has some, some cultural value. We call this pop culture if it is a popular cultural value. Some also call it clickbait. Actually, most of these topics are very popular, say on YouTube, and they are also very, very exciting. There's a reason for it. They are very, very exciting things. So first of all, I start with number 1 and go to number 10, not like in Watch Mojo or so where you start with number 10 to number 1. The reason being you want people to stay until the end. So the fundamental theorem tells us that if we integrate the derivative of a function, then we get fx minus f of 0, and if we integrate from 0 to x ft dt and then take the derivative, then we get just f of x. This is an absolutely fantastic result because it allows us to explicitly compute areas. So we have the integral from 0 to pi sinus t dt. It would be hard to compute this just by summation. So this result has been obtained relatively late. You see Newton and Leibniz there together animated, and they were also a little bit fighting with each other, which makes the whole thing really sweet. For gravity, right? If you want to compute something like you want to see how a stone falls, and you want to actually compute how long it takes until it comes down. Explicit results you can get by solving differential equations, which governs the motion of the planets, the motion of mechanical systems like this one. Also toys like this. Okay, the second theorem which I chose here is Euler's formula. It is remarkable because it joins the exponential function, the cosine and sine functions. It allows you actually to define the cosine and sine functions from the exponential function. So it's a kind of a gateway thing. So what you have is, if you're in the complex plane, if this is the real, this is the imaginary part, and this is x here. So that's cosine x, sine x. So it's trigonometry. It is popular because it combines various things, right? It combines analysis. It combines geometry. So we have lots of different things combined here. It's considered the most beautiful formula in mathematics. A few 100,000 pages of calculus books here, and they really neglect the intermediate value theorem. The intermediate value theorem, maybe because it's so trivial, it's easy, right? It's clear that if you have a function which is negative at some point and positive at some other point, then it has to have a root. But roots are very important. Roots lead to critical points. And these are equilibria. And they are extremely important in applications. And if roots disappear, what happens if roots disappear? Then you have trouble in general. It's catastrophes. So this is one of the topics which has become a very popular thing. In the 80s, it has kind of been so popular that it actually degraded again to kind of people laughed about it because it's of this simplicity. But it's a very beautiful theory. It also is related to chaos theory, bifurcations. What happens when you have roots disappear, right? When you have you take that, you deform it, and what happens is after some deformation, the roots disappear. This can have dramatic consequences and can lead to economic collapses or all kind of things, which sudden changes. So catastrophes. So this is the intermediate value theorem. My favorite application is then of the intermediate value theorem is the wobbly table theorem. You see this table is wobbling. I don't know whether one can see this. This table is wobbling, but the theorem is that I can turn it. I can turn this, and then after some angle, it doesn't wobble anymore. This is a famous problem which at the time of Euler was not known, and Euler was the first who then solved this Basel problem. So it is an infinite sum, and the amazing thing is that it's related with pi. So this is quite an important thing. It's important in number theory, for example. Some people want to know what the probability is that for that two large numbers between 0 and n have no common common divisor, no non-trivial common divisor, things like this. This is also called Zeta 2. So the Zeta function, and so that's some n is equal to 1 to infinity. We mentioned the Zeta function before. This is zeta s, and so this is zeta 2. And if you look at the zeta function, so this is the real and the imaginary part. What happens is this: we actually compute the zeta function here at 2, and it turns out one can also compute it at 4, 6. So you learn that in linear algebra how to do that using calculus. And so one doesn't know formulas for 3, for example. So no formulas are known, no explicit formulas known. For 1, it's infinity. And actually that's something which we are going to look at afterwards here in number 6. So this is the case where it diverges. And the conjecture is that here all the roots are here. Conjectured roots. Roots are on real s is equal to 1/2. So that's a open problem, the Riemann hypothesis. We talked about this before, and that's kind of just an amazing thing that we can compute some zeta function values. And it's also related to some pop culture. S is equal to -1. Then zeta -1 is 1 plus 2 plus 3 plus 4. And this is -1/12, as you can compute when you put it into a professional calculator like Mathematica. Okay, number 5 is the computation of the volume of the circle and the sphere. It's due to Archimedes. Just more than he saw that the sphere has the same volume than the complement of a cone inside so when you look at the cylinder and you draw inside a cone, and everything has radius 1. That's just everything scales. So this is radius 1, this is radius 1 here. He was able to compute the volume of the sphere, 4 pi r³². Several calculus books here. I take here the first book, and then I take the second book. I'm not allowed to glue it. And when I'm doing that, how far can I get all? So this is a kind of the break problems like that. How far can I get? You see, I had difficulties here I had difficulties here even to get to the size of the book itself. Very, very surprising that actually the answer is here infinite. And it's a consequence of this divergence of the harmonic series. So Archimedes was approximating pi with rational numbers. So pi is about, I think Archimedes got 22/7. And one can do that better and better. But the question is there a rational number? And the answer is no. And there are various proofs. And the most elegant proof uses calculus. So E is irrational. This is e to the 1. So that's an approximation of E, rational approximation of E. I mean, it's of the form P over Q. So this is P over Q at very large numbers, P over Q. But there is no kind of a possibility to actually write this number down when you take the limit. But pi to the E, we have no idea. So the next important results, I put them together because this is the idea of generating functions. This one is actually something which hurts for me because when I was a high school student, I was doing experiments with partitions. So you see, for example, how many ways can you write 5? So this is what comes in here. These are the partition numbers. When I was in high school, I discovered the pentagonal theorem, the Euler's pentagonal theorem, but I could not prove it, and there's no way. And actually, with generating functions, this is very easy, almost immediate to show, which is then a recursive way to get these numbers, and they are featured also in the movie, The Man Who Knew Infinity. So Ramanujan had that, and Ramanujan did much more. Actually, Ramanujan even could get the asymptotic ways. He could. Okay, number 9 is Fourier theory, and I put it a little bit down also because it's less kind of maybe appearing less in pop culture. But it's important in applications. For example, when you are listening to a music, or when you look at the video, and this is all compressed in a highly effective way using Fourier theory. By the way, Fourier was with Napoleon, on a trip in the Middle East, and so in the heat. So he was actually investigating the heat equation. So, and if every even one is non-zero, then you have proven Goldbach. So the Goldbach conjecture can be written down in Fourier using Fourier theories. Anything essentially you can rewrite in terms of Fourier theory. So it's a very, very nice thing. So the last thing is related to Fourier theory. This is a function. So if you look at that, that's a continuous function that obviously converges because this is kind of going quite fast to 0. So this is an example of a function which is continuous but differentiable at no point. Let me go fly my drone a little bit outside.